right, let's jump right in. We're going to talk about one of the biggest, most profound, unsolved problems out there. And I'm not just talking about computer science, I mean in all of human knowledge. It's the question of P versus NP. This is all about the absolute limits of what we can compute, what's actually possible, and what might be completely out of our reach forever.
And look, the stakes here are, well, they couldn't be higher. Seriously, finding the answer to this one question could trigger an age of unbelievable progress. But it could also shatter our entire digital world in an instant. So how is that possible? How can one problem hold the key to both a perfect future and, total digital chaos?
Well, it's so important that the Clay Mathematics Institute has $1 million prize waiting for whoever solves it. But honestly, the prize money is nothing. The bragging rights and the impact this would have on civilization, that's the real prize. It's priceless.
Think about it like this. On one side, the promise, we're talking about instant breakthroughs in medicine, creating AI that's beyond our wildest dreams, and solving impossibly complex problems like global logistics in a flash. But on the other side, the peril. Every password, every single bank account, every secure government communication, all of it would become completely vulnerable overnight.
To really get our heads around why, let's start with a simple logic puzzle. Picture a robot at a fork in the road. One way is safe, the other is not. There's a sentry there who either always tells the truth or always lies. The robot gets one question to figure out the safe path. Now that's a puzzle you can solve. But what if there were, say, 100 sentries and a massive maze of paths? Does the problem get just a little bit harder, or does it become impossibly harder? That question, right there, is the very heart of P versus NP.
So to really get this, we've got to back up a little and understand how computers actually think. Because at their core, they're just ridiculously fast calculators, built on ideas that go back more than 150 years. It all kicked off with George Boole way back in the 1800s, who basically turned pure logic into math. Then, the legendary Alan Turing dreamed up the theoretical concept of a universal computing machine. After that, Claude Shannon had this brilliant light bulb moment, realizing you could build all that logic using simple electronic circuits. And finally, Bell Labs created the transistor, making it all a physical reality. You can see how each step built on the last, leading us straight to the phone in your pocket.
And here's the really wild part. Every single thing modern computers do, from the most complex AI to your favorite app, is built from just 3 dead simple logical ideas. And, or, and not. That's it. These are the tiny, tiny building blocks that when you combine billions of them, can solve almost any problem you throw at them.
So how do they actually use these building blocks? They follow something called an algorithm. And don't let the word scare you. An algorithm is just a recipe. It's a precise, step-by-step set of instructions. Think of it like an IKEA manual for a computer. Every single task needs a clear guide to get from point A, the problem, to point B, the solution. Okay, but this is where things start to get really interesting. Back in the 70s, computer scientists started noticing that not all these recipes, these algorithms, are the same. Some problems seemed, well, easy, but others seemed monstrously, fundamentally hard. And that observation led them to create 2 giant categories for problems, P and NP.
First up, you've got class P. The P stands for polynomial time. These are basically what we'd call the easy problems. Things like sorting a list alphabetically or finding the fastest route in Google Maps. Sure, as the problem gets bigger, it takes longer to solve, but the time it takes grows in a predictable, manageable way. It doesn't spiral out of control.
Now, class NP is a whole different beast. NP stands for non-deterministic polynomial time, but you can forget that part. Here's what you need to remember. The defining trait of an NP problem isn't that it's easy to solve. It's that if someone just hands you an answer, it's really, really easy to check if that answer is right. And this is the perfect way to think about it. Sorting a list of names, that's a P problem. Easy to do. But imagine a giant, super hard Sudoku puzzle. Solving it could take you ages, right? It's incredibly difficult, but if I just gave you the completed puzzle, how long would it take you to check my work? Seconds, maybe a minute. You could verify it's correct almost instantly. See the difference? Solving is hard, but checking is easy. That is the soul of an NP problem.
The reason some of these NP problems are so incredibly tough is that their difficulty grows exponentially. For every new thing you add to the problem, the time it would take to brute force a solution just explodes. We're talking about calculations that would literally take a supercomputer longer than the current age of the universe to finish.
So this brings us right back to that million-dollar question. Are all these super hard-to-solve NP problems just P problems that we haven't been smart enough to figure out yet? Are we just one clever algorithm away from making them easy? What if P actually equals NP?
If P does equal NP, our world would be completely unrecognizable. I mean it. In the utopian view, we could solve problems that are basically magic to us right now. Curing cancer, creating perfect economic models, building truly conscious AI. But in the dystopian view, it would be hacker heaven. All modern encryption, the very thing that protects your bank account and keeps the internet running, is built on the idea that some problems are hard to solve. If they suddenly become easy, all of that security just evaporates.
So you can probably see why scientists are so desperate to find a proof, one way or the other. This isn't just an academic game. And the hunt has actually led to some incredible insights about the nature of hard problems themselves.
This leads us to this totally mind-bending idea called NP completeness. Researchers figured out that a ton of these different super hard NP problems are actually just the same problem wearing different disguises. This analogy nails it. It's like a vet suddenly realizing that a tiny toy poodle and a giant St. Bernard are fundamentally the same species. And what this means is, if you could find a fast way to solve just one of these special NP-complete problems, you'd have a master key that could solve all of them instantly. And don't think for a second these are just abstract math puzzles. No, they are everywhere in the real world. Trying to find the most efficient route for an Amazon delivery driver? That's the traveling salesman problem. It's NP-complete. Figuring out the absolute best way to match organ donors to patients, NP-complete. Even becoming a grandmaster at a game like Tetris, yep, that's an NP-complete problem too.
Now, a lot of researchers think the one true master key, the problem to end all problems, is something called Boolean satisfiability, or just SAT. It's a really fundamental question about whether a giant, messy, logical statement can ever be made true. It is so central to everything that if anyone, anywhere, finds a fast algorithm for SAT, they've done it. They will have proved P equals NP, just like that.
But so far, nothing. Not even close. In fact, the search has hit so many dead ends that it's accidentally created a whole new field of study called meta-complexity. Researchers are now asking this really strange, navel-gazing question. Why is it so incredibly hard to prove that these problems are hard? They're literally studying the complexity of complexity itself.
Which leaves us with this one last incredible thought. You know, most experts are pretty sure that P does not equal NP, but proving it seems almost impossible. So, will human creativity finally be the thing that cracks the code? Or, in the ultimate twist, will we end up building an AI that's smart enough to solve it for us? And if it does, would we even be able to understand its answer?